Welcome. In this short video, we will look at the complete solution for the example 2 in chapter 5.5, which is AC power. Okay, so let's switch to the class notebook. And this is example 2. Now, in example 2, we are given one source. It's a voltage source, even though it doesn't state V, but it's a voltage source indicated by the plus and minus signs. And then we have two loads, A and B. Okay, the only information we are given is that the power associated with each load is 10 kVA and 5 kilowatts respectively, not with each load. 10 kVA is associated with load A, 5 kilowatts associated with load B. In addition, we are given the power factor. For A, load A, power factor is 0.5 leading, or we could say it's 50% leading. Load B, power factor is 0.7 lagging or 70% lagging. Okay, we are asked to determine the power triangles. So draw the power triangles for the load, determine the total complex power for the source, which is right here, and then power triangle for the source. So let's begin. First things first, we'll set up the problem and then we will do the calculations. So extract as much information as we can from the provided circuit diagram. Let's tackle load A first. Load A has information 10 kVA, right? From 10 kVA, and the power factor is leading. Now, it's a leading power factor. It means it is a capacitive load. Eli the Iceman, the current leads the voltage in a capacitor. So power factor leading, or a leading power factor, means the load is capacitive. All right, the load is capacitive. So the power triangle should look like this. Negative Q, right? Negative Q. So the notations I'm using are a subscript of A, right? So on the real axis, or the positive real axis, we have the real power P, subscript of A, and in the negative, oh, sorry, this should actually be here. And the negative imaginary axis, we have QA, right, which is the reactive power associated with load A. And on the hypotenuse, the third side of the right angle triangle, we have SA, or magnitude of SA, which is the total complex power associated with load A. Okay. Now, think of this. It is a right angle triangle, right? Right angle triangle, and it has four quantities. The three sides, P, Q, and S, and then phase angle theta. This is the power angle. Theta is the power angle for this particular triangle. So in order to find any of the four quantities, we need at least two. And we are provided with two quantities. We are provided with the magnitude of SA. And we know it is the magnitude of SA because it is given to us in units of VA, volt ampere, right? If it was P, it would state watts. If it was Q, it would be VAR. SA is the only quantity with units of volt ampere. So again, 10 kilovolt ampere kVA indicates that it refers to magnitude of S. At the same time, watts indicates it is real power P for load B. Okay, load B. So load B has a lagging power factor. Lagging power factor indicates it is an inductive load. Eli the Iceman, current lags the voltage. So again, remember, power factor is always with reference to the current. If current leads the voltage, power factor is leading. If current lags the voltage, then power factor is lagging. So inductive load, I lags V, right? And so 0.7 power factor lagging indicates it's an inductive load. So power triangle looks like this. Real axis or positive real axis, we have PB, which is the real power associated with B. And on the positive imaginary axis, we have QB, reactive power associated with B. We again have a right angle triangle, 4 quantities. We need only 2 to find the other 2, right? So in this case, we are given 5 kilowatts. So P is 5 kilowatts. And in both cases, we are given the power factor. So we are given the cosine of theta. We can find the power angle from the power factor. So that is basically our setup. We are setting up the problem. We set up the problem correctly by extracting information that is provided to us. Now we will perform the calculations. So for load A, power factor is 0.5. Cosine of theta, the power angle is 0.5. So theta is 60 degrees. 60 degrees. Now, real power P can be given by this equation, VRMS, IRMS times cosine of theta. Voltage is the same for all 3 components, again, because they are in parallel, right? So voltage is the same. Voltage remains the same. Current changes. So VRMS, this V indicates the voltage across all 3 components. IARMS solely refers to the current that is flowing through load A, right? IA. So real power for load A can be given by VRMS, IRMS times cosine of theta. We already have the magnitude. Magnitude S gives us, or from that equation is IRMS, VRMS is the third side of the right angle triangle, right? So simple multiplication, 10 kVA, 10,000 times the power factor 0.5, cosine of theta is the power factor. So PA is 5,000 watts. As straightforward as that, one-step calculation. Reactive power is the 4th quantity. That's given by, again, VRMS, IRMS times sine theta. So again, magnitude of S, which is 10,000 times sine theta, gives me 8,660.25 volt ampere reactive, VAR. Do not forget your units. Now, since this reactive power is associated with the capacitor, we indicate it with a negative sign, right? It's a negative sign. It's in the negative imaginary axis. Now let's tackle load B. Load B, power factor is given to us as 0.7. Again, apply the same equations. Power factor is cosine of theta. So cos of theta B is 0.7. So power angle for load B is 45.57. 45.57. Now, using trigonometric identities, I can write tan of the power angle, tan theta is Q over P. Q over P. Again, principles of trigonometry, right angle triangle, tan of theta would be Q over P. So from there, I can write QB can be given by tan of 45.57 times 5,000. 5,000 is the quantity that was provided to us in the problem statement, 5 kilowatts, right? So QB is given by tan of 45.57 times 5,000, comes out to be 5,101.02 volt ampere reactive, VAR. Okay, VAR. Now, from all the equations available to us, again, we can pick and choose which ones we want to use. Again, we'll apply rules of trigonometry, Pythagoras theorem. Magnitude of S, the hypotenuse, is equal to root of the square or the sum of the squares of the 2 sides. So S is equal to root of P square plus Q square. Plug in the values and solve, and you obtain magnitude of S as 7142.86 volt ampere, VA. Now, we have determined all values for both loads, meaning both power triangles. If we add up all these values in the loads, that has to provide us everything that is supplied by the source. And so source, again, the subscript of S is equal to P plus JQ. So SS is equal to PS plus JQS. PS would be given by the total sum that is being provided to the loads A and B. And so PS can be written as PA plus PB, gives us 10,000 watts. QS, of course, again, the sum of the reactive powers, but have to take into account that QA deals with a capacitive load. So reactive power for a capacitor is negative. Again, power in real life is never negative, right? Just as it is not imaginary. It's a mathematical representation. It's a mathematical representation for us to be able to balance out equations, right? And so QA has a minus sign. We put it minus 8,660, and QB, which is inductive load, is plus. You add up both of them together and you get minus 3,559. We've talked about power factor correction, where the inductive load, the requirements for the reactive power for the inductive load is offset by the power provided locally by the capacitor. But in this case, the capacitor is actually has a power requirement that is larger than the inductor. Okay, so overall, we can say that the total power in that source or provided by the source is negative, and hence the source power angle will also be negative. Now we have the power angle, we have the total power that is being supplied by the source, we have the total power that is being supplied for the real power as well as the reactive power by the source, right? PS and QS. We also have the phase angle. All we do now is find the phase angle. Okay, so to find the phase angle, we take tan of the angle, which is tan theta, given by Q over P, and that gives us an angle of minus 19.59. So minus 19.59. Okay, again, trigonometric identities. It's a vector quantity, right angle triangle, three sides of a right triangle plus the phase angle gives us 4 quantities. We can find any 2 quantities if you're given the other 2. Okay, so power factor for the source would be the cosine of this angle, comes out to be 94.21%. And because it is negative, it refers to a capacitive load, and hence power factor is leading. Okay, power factor is leading. You add up PS and QS, right? And that gives us the total complex power supplied by the source. So it's 10,000 minus J 3,559.23 volt ampere, VA. In polar coordinates, we can write it directly as 10,614.52 magnitude of S, which is the third side of the power triangle with a phase angle of minus 19. And so the source power triangle looks like this. On the real axis, or the positive real axis, we have PS, 10,000 watts, and the negative imaginary axis, we have minus 3,559.23 volt ampere. SS, the magnitude of the total complex power, is 10,614 volt amperes. And that is how we can solve for the total source power. Review the problem. Okay, review the video. Make sure you note down any questions you have and send them to me. All right, reach out to me. I'll be available all day tomorrow, in person as well as Zoom. But this is an important topic. So again, review this video as soon as possible and contact me in case you have any questions. And I will see you in class on Friday.